Hi, hello everyone. This is Rajaram, Assistant Professor in the Department of Artificial Intelligence and Machine Learning from St. Martin's Engineering College. Today we are discussing multiplication algorithm and Booth multiplication algorithm in computer architecture. So you know already what is the multiplication. Multiplication is a method. It can multiply two numbers and we will get this some product. So it computer architecture we have convert to binary and we can do the multiplication, and based on the computer architecture we have calculated all the values and we will get a product value of binary numbers. So here first we have discussed multiplication, general multiplication in computer architecture. So this is the general multiplication. So here we are taking two example numbers, those are 23 and 19. So 23 has converted to binary, that is 10311, and 19 has converted to 10011. So it was called as a multiplicand and 19 has called as a multiplier. So then we have to do the multiplication and we will get 437 a binary product number at general multiplication. But at computer architecture it is not possible. So based on the circuit only we have to process and we will get output on ALU. So here first we will discuss hardware implementation of the multiplication algorithm. So here we are taking two types of products. Those are 23 and 19. So 23 as a multiplicand stored in B register. So multiplier can stored in Q register. So here we have taken one more register, that is AC accumulator. It is a general purpose register. So here we are getting output purpose, we are using accumulator register, and always it is at initial stage always 0. So as well as the sequence counter has do the sequentially do the process of bits flowing at registers. So at parallel ladder we do the ALU process, arithmetic logic unit process, and do the process and we will get output at the accumulator. So here we are using one more E. So E is a effective address. So if doing the process, if any additional bits are carrying, means we have stored that data, that bits in effective address at E. So based on this hardware implementation only we can do the process and we will get output at multiplication data. So here we are taking LSB. So LSB means least significant bit of the Q register. So this based on this Q register least significant bit data, based on this data only we have to process and we will get output at multiplication process. See here flow chart of the multiplication algorithm. So this is the flow chart of the multiplication algorithm. Already we discussed multiplicand stored in B register and multiplier can stored in Q register. So here the conditions are A can read the data from Q exclusive or B data. So Q exclusive or B data. So Q can read data from Q exclusive or B data. At A always at initial stage 0 and as well as E also 0. So up to sequence counter can counting n minus 1 operation. So for example we have taken 5 bits, means so 5 to 4, 4 to 3, 3 to 2, 2 to 1 and 0. Up to 0 process will be done by using the sequence counter. So next condition. So what is the condition at here? So already we discussed hardware implementation Qn. So Qn is if Qn is equal to 0, means we will get a product of both register data, both multiplication data. So if it is 0, means direct we can do shift to right EAQ operation. Shift to right EAQ means we can shift one bit to next bit of operation. So up to sequence counter minus 1. So up to sequence counter minus 1 means up to 0. Either condition is equal to 1, means Qn is equal to 1, means we can add B bit data to A. So B bit data to A at effective address. So here B can add it to E, and then next we can do same as a sequence shift to right operation EAQ, and as well as up to sequence counter minus 1. Then here we are getting the output of product. So if sequence counter is equal to 0, the product will be done. So if sequence counter not equal 0, again we have send to data to condition. So what is the condition? Qn. Again we have do the process up to Qn is equal 0 and we will get a product of EAQ. So finally the product is AQ. So finally the product is AQ. So see here next example of the multiplication algorithm. Here we are taking two numbers, those are 23 and 19. So 23 is stored in B register. So 19 can stored in, this is the multiplier. This is a multiplier. So multiplier can stored in Q register, and as well as already we told A is initial stage always 0 and E also always 0. So here up to how many bits are there? 5 bits there. So 5 bits means the up to sequence counter 5. So we can start at 5 to 0. So 5 to 0 condition we can start it. So here, so what is the Qn? So Qn, so Qn means least significant bit of the Q data register. So Qn means here Qn is equal to 1. So Qn is equal to 1 means first we can do the add A plus B, right? So we can add B register data to A. So here we are added 1 0 1 means B data to A. So finally here we are getting the data. So finally we are getting the data. See here example we are discuss. So B is equal to 1 0 1, right? At the initial stage E A Q SC. So SC is a 5. So this is 1 0 0 1 and it is always 0 and E also 0. At here Qn is equal to, here Qn is equal to 1. So means we can add B to A. So what is the B? 1 0 1. So 1 0 1 means, so here 1 0 means 1, 1 0 means 1, 1 0 means 1, 0 0 0 0 1. So E as well as here, and Q also came to here, right? Then next we can do shift to right EAQ, shift to right EAQ operation. So shift to right EAQ means we can shift to this bit to here, and this one can shift to here, this 0 can shift to here, this one can shift to here, this one can shift to here, and this one can shift to here, this one can shift to here, 0 0 1. So here this one can be discarded. So finally at fifth position, so finally the product is 0 0 0 1 1 1 0 0 1. So completed. Next coming with fourth sequence counter. So fourth sequence counter, what is the last least significant bit? So here Qn is equal to 1. So Qn is equal to 1 means we can add B bit to A. So again we can add B bit to A. What is the B bit? 1 0 1 to here. So 1 1 0 and 1 can carry to here, 1 1 1 is there, 1, and here 1 can carry. So 1 1 0. So here 1 can carry 1 and 1, right? E is 0, right? Next we can do shift to right EAQ. Shift to right EAQ operation. Again we have shifted to 0 here, 1 can shift to here, 1 can shift to here, 0 can shift to here, 1 can shift to here, and as well as this has printed to here. So this 0 can shift to here, this 1 can shift to here, this 1 can shift to here, this 0 can shift to here, this 0 can shift to here. So this one can be discarded. Now coming with sequence counter 3, right? So coming with the sequence counter 3. See here. So sequence counter 3 at Qn is equal to, Qn is equal to 0. Means here Qn is equal to 0 means direct we can do shift to right EAQ operation only. We can do shift to right EAQ operation only. So here 0 is there, 1 1 0 1 0 1 1 0. Now we can do the shift EAQ 0. This is 0 can shift to here, this 0 can shift to here, and so here one can sorry 0 can shift to here, this 1 can shift to here, this 1 can shift to here, 0 1 0 1 1 and 0, this 0 will be discarded. Next coming with second here, so like that only all the process we done and we have get the product at here. So finally we can get AQ of product. So what is the product? 0 1 1 0 1 1 0 1 0 1. So finally we'll get output of the both A register and Q register data is called product of the this multiplication data, right? So next we have discussed Booth multiplication algorithm. So Booth multiplication algorithm means two signed magnitude data. So if we have given a negative numbers to computer, so computer can read only positive numbers. So either a 0 or 1 only. So why? Because of the computer can do the process based on the binary numbers only. So if you are given a negative numbers means, so you can do 2's complement at Booth algorithm. So Booth algorithm by based on the this Booth algorithm only we can do operation of 2 multiplication. So see here example of hardware implementation of Booth multiplication algorithm. So here B register same as well as multiplication algorithm. So here we have stored the multiplication data, and at Q register we have stored the multiplier data, and AQ AC register. So this is accumulator general purpose register, and we will get both A register and Q register product of the output. So here complementary and parallel adder will be processing at ALU. So complementary, why we are taking complementary at here means we can do the 2's complement. So signed magnitude data means signed magnitude 1's complement and 2's complement. Because of here we are taking negative numbers. So that's why we are using Booth multiplication algorithm. So sequence counter can count the all the algorithm all the sequence bits and do the process. So this is the flow chart of the Booth multiplication algorithm. See here same as multiplication stored in BR register, multiplier can stored in QR register. So here accumulator is 0. There also A always 0 at initial stage. AC is 0. At here Qn plus 1 is 0 and sequence counter is up to n bits. So up to n bits we can count the sequence counter. So here we are taking Qn plus Qn plus 1, 2 bits we are taking to here. So if Qn is equal to 0, Qn plus 1 is there. So we can do add the data B data to AC. Then here 1 Qn is equal to 1, Qn plus 1 is equal to 0 is there. So here we can do the 2's complement, right? So here just we can add the data to accumulator. So here we can do the 2's complement for the B register. So and then we can do arithmetic shift right operation. So arithmetic shift right operation means first bit as well as it can print, and then next we can move to the next bit. So later we will discuss. So then we can do arithmetic shift right operation up to sequence counter minus 1. So if both Qn and Qn plus 1 is 0 or both can high impedance 1 1. So direct we can do the arithmetic shift right operation, and next go to the sequence counter is 0, we will get the product. If not sequence counter is equal 0, if again we can send to condition. So then up to yes sequence counter is equal 0, up to we can get the product, we can do the process. So this is the arithmetic shift right operation. So based on this shift right operation only we can move the bits and we can do operation and we can get the product. So see here some bits are we are taking, right? So here we are taking some bits, and as well as here also some bits are print. So at arithmetic shift right operation, what is mean? So first what we are taking the here bits, it will be print on first bit of the here, and as well as this bit can print to the second. Then this bit can move to the here, and this bit can move to the here, and this bit can move to here, and this one like that. So it was shifted to, and at here we are discarded to the last least significant of the bit of this first operation. This is arithmetic shift right operation. And next coming with Booth multiplication of example. So here before we can take both positive numbers, but we are taking two negative numbers, and we will get a positive number of 177, right? So here we are getting positive number of 177. So both can be negative numbers. So both can negative numbers means first we can do the 2's complement of 9. So 2's complement of 9 means, so this is the 9's minus 9 value, and minus 13 value, sorry. So this is 13 value, and 9 value is QR data. So at the initial stage always AC is 0, and Q can store the 9 value, so 10011, and here we can done the 13 value. So 13 value 10311 can do the 2's complement, and we will get some complementary data. So that is BR bar plus 1, so that is 010011. So here Qn is equal to 0, and Qn plus 1 is equal to 0, and Qn is equal to 0 at fifth sequence counter. So fifth sequence counter, here based on these bits only we can do the process. So if Qn is equal to 0 and Qn plus 1 is equal to 0. So here Qn is equal to 1 means we can do the subtract, subtract means BR bar plus 1. So we can do the subtract operation of BR. So then we can add to AC. So AC, what is the 01001, and we will get some product, right? So we can do the some product. Then next we can go to the arithmetic shift to EAQ. Arithmetic shift to EAQ, right? So here E is 0, then we have moved to the next bit, and so here we can move this 1 to here, and this 0 and this 0, and this 1 can move to the here, right? So like that only this 1 can be moved to here, this 0 can move to the here, and this 0 can move to the here, and this 1 can move to the here, this 1 can move to the here, and as well as this 0 will be discarded to at here. Next, so what is the Qn plus 1? So Qn plus 1 is 1, right? So Qn plus 1 is 1, and Qn is 1. So both 1 means we can do direct arithmetic shift right to EAQ, right? So direct we can do the EAQ shift to arithmetic shift right EAQ. So here 0 will be added to first bit, and then this 0 can move to here, this 0 can move to here, and this 1 can move to the here, this 0 can move to the here, this 0 can move to the here, 1 can move to the here, 1 can move to the here, 0 and 0. So this 1 can move to the at here. So here the 1 is discarded. So next coming with sequence counter 3, and this is sequence counter 4. So here Qn plus 1 is 1, and Qn is 0. So 0 1 means we can add B data to AC data. So BR data can add it to accumulator data. So generally here what is the accumulator data? So 00010, right? So that 00010, so we have added B data to 00010, so that is 10111. So 10111 can add it to this accumulator, and we will get some product, right? So we will get some product. So here 01110, this one can carry to here. So 11 means here 0, and again we have 1 can carry to here, that 1 can print to here, and this one can print to here. So you will get data. So next, what is our step? Arithmetic shift to right EAQ, right? Arithmetic shift to EAQ, right? Again, so here what is the sign bit? 1. So sign bit 1 means it is a negative number. So negative, what we are getting the here, so when arithmetic shift right can print to here, and this one can shift to next bit, right? So in example, so for example 10111 is there, right? So 111 there is means at arithmetic shift right operation, as well as it can print to here, and this one can print to the second bit also. Then this 0 can move to third bit, this one can move to the fourth bit, and this one can move to the here, this one will be discarded, right? So like that only we can do the arithmetic shift right. So if shift right EAQ means just we can move to the one bit for right only. At arithmetic shift right means we can print first bit for here, and as well as this one can move to the second bit also. So based on this arithmetic shift right only, we can do the process, right? So like that only we have getting the data at sequence counter 3. So what is the product of it here? 11100, right? So like that only finally we have getting AC and QR data for the product of our multiplication data. So see here 00011 101 and 01 is for 117, right? So next we have going to the video session, right? See here. So first for multiplying operation, so multiplying operation can store the 2 bits in 2 register. Those are multiplicand stored in B and multiplier can stored in A. So multiplicand stored in B and multiplier can stored in A. So based on this flow chart only we have do the process at computer architecture. So here AS means A sign bit. So A sign bit can store from the data Q exclusive or B. So Q exclusive or B sign bits can stored in A. So A always 0, right? So A always 0. After when the doing the process, the output data will be stored in A. So here QS. So Q sign bits. So Q sign bits means, so Q sign bits can exclusive or B sign bits. So this is one also we can stored in Q register. So A is 0 at initial stage and E also 0, right? So it is the initial stage A0, E0 and sequence counter is n-1 up to n-1. We can do the process at multiplication algorithm. So this is the condition. So condition is Qn. So Qn is equal to 1 means we can add B register data to A, right? And next we can do this shift to right EAQ and we can do the shift to right EAQ and up to sequence counter -1. If a sequence counter is 0, we will get the product. If a sequence counter is not equal 0, again we can pass data to condition. So here, see here, so multiplicand stored in 1011 multiplier and multiplicand stored in Q register, and A is always at initial stage always 0, E also 0. So sequence counter how many bits? 5n. So 5 process will be going on at here. So sequence counter is 5. So here Qn is 1 means, so Qn is equal to 1. So we can do the add operation for B is added to A. So B is added to A. So we will get some output, and then next we can do the shift to right EAQ. So shift to right EAQ means this 0 can move to right bit and this 1 can move to here. This 0 can move to next bit. So like that only we have moved. So here finally this 1 can be discarded. Then fourth sequence counter. So fourth sequence counter also Qn is equal to 1 means, so we can add operation. We can do the add operation. So A will add it, sorry, B will add it to A. So then we will get the some output, and next we can do the shift to right EAQ. So shift to right EAQ means we can shift 1 bit to right. So one bit to right, and we will get some output. So here, and next coming with the sequence counter 2. So sequence counter at 2 Qn is equal to 0. So Qn is equal to 0 means we can direct we can do the shift to EAQ, right? So here shift to right EAQ, right? So here Qn is equal to 0. So Qn is equal to 0, shift right EAQ to, we have moved to 1 bit for right, right? Next coming with the sequence counter 1. So sequence counter 1. So what is the Qn? So Qn is 1, right? Qn is 1. So Qn is 1 means again we can do the add operation. So B can add it to A. So B can add it to A, and we will get some output product. And here again we can do the shift to right EAQ. So shift to right EAQ means we can again move to right the bits. So this is 0 and this can 1, and 1 can move to right and 0 can move to here. So like that only here we can done. So finally we have get the output of AQ is the final product of the multiplication of two numbers. That is here. So this is Booth multiplication algorithm. Booth multiplication algorithm can be invented by Andrew Donald Booth. So based on his algorithm only we have do the process at here. So here we have taken 9 into 2. So 9 into 2 means 18 bits, right? 18 bits. So here, see here, A q is equal to 0, qn minus 1, m, and action will be going on it here. So action will be going on it here means it is always 0, A register, and here we have done the operation. So here A data will be 0, so q data we have stored 2. What is we are taking it there? 2 into 9. So 2 into 9 means 18. So 18 will be get at here. So what is our product? 18. So right. So 2 can stored in q register and 9 can stored in m register. Right. So qn minus 1 is 0. Right. At initial stage qn is equal to 0 and a also 0. Right. At initial stage we are getting some output, and next we have what is our operation. So qn is 0 means direct we can do the arithmetic shift right operation. Right, arithmetic shift right operation means 0 can print to here, this 0 can move 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 to here, 0, 0 and 1 can move to here. So this 0 will be moved to here. Right, so it is always m can print the same as at here, and shift right operation will be done. Then and at second step, right, at second step qn is equal to 0, qn plus 1 is qn is equal to 1, q is equal to 0. Right, means here we can add b data to a. So what is the b here? 1 0 0 1 1 can add it to here. So why we are added to this one means the 2's complement will be going on to here. So here 0 1 1 1. So after the 2's complement we will get the output here. So here 1 why? Because of the sign bit will be 1. So 1 can print to here and 0 can print to here, and 1 can shift to right and 1 can shift to right, 1 can shift to here, 0 0 0 and 1 can shift to here at the third step. So at third step, so a is 1 0 1 1. Q is equal to 0 means 1 0 0 and q minus 1 1 and m is equal to 1 0 0 1. Right. After the shift right operation, so after that shift right operation 0 1, right, 0 can move to here. Right, like that only we can do the all the process and we will get product at Booth multiplication algorithm. This is the fourth step. So at fourth step a is 0 0 1 0 and q is 0 1 0 0 and q minus 1 is 0. Right. So based on these operations only we have getting the output. Right. So finally we get output at here. So what is the output at here? A plus q. So a plus q means, see this, a plus q. So a plus q, the 0 0 1 0 and 0 0 1 0 we are getting. So what is our example? What is our example? 2 minus 2 into 9. So 2 into 9 is 18. So 18 is there 1 2 4 8 16 and like that only we are given. So 16 plus 2, so 18. So finally we will get the output 18. So like that only we have discussed multiplication and Booth multiplication algorithm, and based on that circuits only we will get the output at the computer architecture. Right. So overall we discuss multiplication and Booth multiplication algorithm. So here very simply at here. Right. So based on these circuits only we can do the process. So first of all we know this hardware implementation for the multiplication algorithm. So hardware implementation nothing but circuit diagram of the multiplication algorithm. So this process all will be going at ALU. So based on ALU only we will get output. So ALU will not work means we will not get the output. So here hardware is a must and should we know. So here we are taking B register, accumulator is general purpose register, Q is multiplier register, so B is a multiplicand register, and here parallel adder and complementary. So there is doing it process at ALU. So based on this parallel adder only we have to do the process at central processing unit. So sequence counter. So sequence counter can count the sequentially numbers, so bits. So here least significant bit. So least significant bit is based on least significant bit only we can do the process. So based on a least significant bit, so least significant bit is 1, it is a negative number, so we can do the add operation to A, right? So if significant bit is 0, so we can do direct shift to right EAQ operation. At both multiplication, direct based on Qn and Qn plus 1. So both Qn and Qn plus 1. So Q register up to n bits we are flowing, and as well as Qn plus 1. So it is additional flip flop. Already we discussed at E. So E is additional flip flop. So when carry the bits, so we can store the data at Qn register. So based on this both hardware implementation only, we will get output of positive numbers and negative number product of by using the multiplication algorithm, right? Thank you so much.